Well, everybody, hello there. So this is part 3, the end of our review for the test. So first off, number 3, where do the following elements, hydrogen, the smallest element, carbon, let the bell ring, fairly small element, and then gold, a big element, where do they come from? Well, in class we talked about looking at this periodic table, and pretty much here's what happens. Hydrogen was formed at the moment of creation, known as science as the Big Bang. So we'll call this the Big Bang, moment of creation. Yeah, a silly term, and there was no, okay, anyway. Carbon. Now carbon it's going to be a smaller star that can form this. Pardon me. So carbon's going to be formed from small stars, excuse me, small to medium-sized stars. Now, obviously, big stars can make it too, but carbon is fairly small element. So, for the most part, any elements in the very top can be made by a small star, but pretty much the body of the periodic table, it's going to come from, in this case, like gold, it's going to be large stars. And large stars are hot, and we're talking large main sequence stars. And when they end their life cycles, they end so with a bang, and that's called a supernova explosion. And in the process of supernova, you can have things like carbon and helium can join together and make bigger elements. You know, they can make sodium. Those get slammed together with other elements. Maybe you've got some fluorine over there, and they step and build up. This all happens in moments, and you can end up connecting together like a bunch of chemical Legos, elements that are huge like gold. So the really big elements, most of the elements on the periodic table are formed in the core of supernova. Since we have all of these elements here on Earth, that means that all these elements had to be created in a very hot blue star that existed in our region of space more than 5 billion years ago, because that's about the time our sun formed, probably from the remains of the exploded supernova. There. Now, the HR diagram compares what two factors? Well, an HR diagram in its simplest form, it is comparing brightness. On this chart, we've got this labeled as brightness. Sometimes they may call it luminosity, magnitude, but it's how bright a star is compared to its temperature, how hot. And there's different classifications. Sometimes I talk about spectral classification, but it comes down to the left side of the chart, really hot. As you get over here, really cold. And we get this, most stars fall along what we call the main sequence, going from the bigger blue stars over here, and then as these stars get to the bottom of the chart, they tend to get cooler, only 2,500 degrees, hot to us, but for a star it's cool, but fairly faint. The brightness here is listed as like a 10,000th. So these stars are not very big, and they're fairly cool. And then you got cores of stars after they've blown up over here. These are white dwarfs and neutron stars. A lot of stars, when they end their life cycles, they're going to start they're going to fuse helium now. And when they start to fuse helium, they start to get bigger, and they'll form these giants. So these giants are just temporary stars that are really in the process of dying, and once they get done blowing off all their energy, they'll end up being just a little tiny core here. So, the HR diagram compares what two factors? Temperature, and we got high temperature to low temperature, and then we've got brightness. I'm just going to call brightness. We've got low brightness and high brightness over here. So the blue stars up here are hot and bright, and then the little red stars over here, they are fairly low temperature, and they're not very bright. They don't give off a lot because they're not that big. They can't give off that much. Lastly, the last of our questions here. Earth's internal heat comes from what three sources? So we've got our planet Earth here, and we had a reading passage, and you can review this and why is the Earth's core hot. And really, the first paragraph tells us heat from when the planet formed, and frictional heating caused by denser material sinking and rising. We've got a little diagram here kind of showing like when you got boiling water, you've got the bubbles where they get lighter, they come up, and then they sink back down. Well, in the When we get really hot elements, they tend to expand a little bit. They rise up, they cool off, they sink. So we get these little convection currents in there. And heat from the decay of radioactive elements. So we get some fission going on. Fission splits right down the middle. You got big particles breaking into smaller particles, so nuclear decay. We've got convection currents of things rising and sinking and going up, and the friction of that causes some heat, some friction there, so we get these little convection currents going inside of there. Pardon me. And then the heat, the leftover heat of formation. So when the Earth was a whole bunch of particles coming together, small planetoid-sized things, and then bigger chunks and moons, they still had some residual heat from the solar system, and these hit each other. You know, they give off some heat, and they're bumping and rubbing, so you've got the heat of formation. And after about 4 billion years, we end up getting, you know, our planet has been fairly stable. It's cooled off on the outside, but we still have a lot of heat from the heat of formation. Oh, that should be formation. We've got the heat of friction because we've got all sorts of stuff going on inside of here, things bubbling up and down. That's where we get, sometimes these pop out and you get volcanoes. And then we got nuclear reactions going on inside of the core, things like uranium changing into smaller elements. So there you go.